Hello and welcome to part 4 of this lecture on the halogens. Moving on, we'll be looking at the testing for halides in this session. The halides that are being tested are the chloride, bromide, iodide. They're usually taken as aqueous solution. So let's say if you have sodium chloride or potassium iodide, etc., it's dissolved in water to get an aqueous solution, and then it is tested. So to this halide solution, what we'll be doing is we'd be adding dilute nitric acid first to remove any carbonate anions that could be present. If there are any carbonate anions, it interferes with this test. So we need to convert that into soluble nitrates. So you do that. So you add a few drops of dilute nitric acid, and then you add silver nitrate. Now the silver nitrate would react with the halides and form the insoluble silver halides. That is, if there's chloride, you'd get silver chloride, silver bromide, silver iodide, if iodide is present. And these ones are insoluble, and hence you see them as precipitates. Not just precipitates, but they also have characteristic color. Silver chloride is white, silver bromide is cream, silver iodide is yellow. Okay. So this is your equation. Let's say I've done it with sodium chloride. You can do it with whatever chloride, bromide, iodide that you need. So you look at it and you identify that the cation silver has gone with the anion chloride, while the cation sodium has gone with the anion nitrate. So you have the cations and anions exchanging their partners, and this is what is called as a double displacement reaction. It is not redox because on either side you find that the oxidation states remain the same. The net ionic equation is basically the Ag plus aqueous cation combining with the Cl minus or the Br minus or the I minus aqueous anion to give you the silver halide, AgCl, AgBr, or AgI, which is a solid. Okay, so in your RGCSE or your GCSE chemistry would kind of stop here. The color of the precipitates, the formation of the precipitates. Okay, now AS level kind of goes one step further, because in real life, if you are actually doing a chloride, bromide, iodide, all three of them side by side at the same time, then it is easy for you to compare the colors. One looks obviously very white, one looks pretty much yellow, and the one in between, okay, you assume that it is green. But there are two problems. One is if you have colorless solutions, for example, say if you start with sodium chloride, then yes, identifying it as white, cream, and yellow is easy. But what if the salt is already colored? What if, say, it is copper chloride? Copper chloride is green. Then we have trouble, all right? Because the color of the precipitate is not very clear. That is one. The other thing is, if you just have one unknown halide salt and you do not know whether it is chloride, bromide, or iodide, and you do a test, the white may not be pure white. Cream kind of looks yellow. So there could be confusion. So to confirm it, what we do is we further add aqueous ammonia to the precipitate formed to test for the identity of, or to identify the halide. Because the white precipitate, silver chloride, completely dissolves in dilute aqueous ammonia, giving you a colorless solution, while the bromide and the iodide precipitates are insoluble. While in that case, if it is insoluble, okay, if the precipitate is insoluble in dilute aqueous ammonia, what you do is you add concentrated aqueous ammonia, in which case the bromide would dissolve, but the iodide remains practically insoluble. Now, what is the solubility about? It's about this reaction, okay, even though your syllabus tells us that you don't have to know this. I mean, this is as part of your A-level syllabus, so it doesn't harm to know this thing. What happens is the AgCl combines with the NH3 to form this sort of a complex, okay? This is called a complex ion, which you'll be studying in detail. But it forms this complex, and this is soluble. Now, if you see clearly, this is a, an equilibrium process. The AgCl, the position of this equilibrium is far towards the right-hand side. So even with a low concentration of ammonia, this reaction occurs. While AgBr and AgI, the position is a little towards the left. So AgBr, you are able to push this equilibrium towards the right by increasing the concentration of the ammonia, while AgI, the position of equilibrium is so far towards the left-hand side that no meaningful increase in concentration of ammonia is able to push that equilibrium, okay, enough to the right-hand side. Okay, as a result, you find that AgI is insoluble even when you add excess concentrated aqueous ammonia. Okay, now a word of caution. Here, your theory kind of talks about dilute aqueous ammonia and concentrated aqueous ammonia to test for the solubility. When you go for your AS level practicals, all right, when you go for your AS level practicals, you will find that you don't necessarily have dilute aqueous ammonia or a concentrated aqueous ammonia in your laboratory. You were just given one aqueous ammonia solution, and usually it is of 1 mole per decimeter cube concentration. Okay, usually you don't get a dilute and a concentrated aqueous ammonia separately. You're just given a dilute, you're just given a concentration of 1 mole per decimeter cube aqueous ammonia. Now, that is why if you look at the tests, right, given at the end of your practical paper, it does not talk about diluted and concentrated. It just talks about the precipitate for chloride being soluble, the precipitate for bromide being partially soluble, and the precipitate for iodide being insoluble. So when you do your practicals, please remember that you need to add, you allow the precipitate to stand and you note down its level, you mark its level on the test tube. Then you add a lot of excess aqueous ammonia that you were given in the laboratory, shake it well, and then you check, allow the precipitate to settle again and check. Did the precipitate dissolve completely? Or did the precipitate dissolve a little and hence the level of the precipitate is decreased but not completely gone? And with iodide, you find that the precipitate level is pretty much the same as before. Okay. Now, why is there a difference between the theory and the practical work in this? Simple reason is we can't afford to kind of prepare different concentration solutions of different concentrations of ammonia. So you use your standard 1 mole per decimeter cube 1, and you play around with your understanding of the theory. So dissolves, insoluble, insoluble, and then dissolves and insoluble turns into dissolves for chloride, partially soluble for bromide, and insoluble for iodide. All right.